For decades, astronomers pointed massive telescopes at the night sky, scanning distant star systems for any sign of a planet resembling our own. The objective was to locate worlds inside the habitable zone. This is a specific orbital boundary where temperatures allow liquid water to remain stable on a planet's surface. But mapping a rocky planet at the correct distance only proves that liquid water is possible. Because these exoplanets are trillions of miles away, humanity has no physical way to sample their soil, test their atmospheric chemistry, or verify if anything is actually living there. The sheer scale of deep space has forced a practical shift in planetary science. The most promising environments orbit our own sun. Proving the existence of life now depends on engineering, the ability to build machines that can physically extract chemical evidence from our immediate cosmic neighbors. Mars is the most scrutinized world in our solar system because its crust preserves a record of a watery past. Geological evidence shows that billions of years ago, ancient riverbeds and large lakes shaped the planet. But when the first landers touched down, they documented a dead world. Mars lost its atmosphere over time, leaving a freezing surface entirely exposed to intense solar radiation. If any microscopic organisms survived that planetary collapse, they could not remain exposed. They would have retreated deep underground, using the rock itself as a radiation shield. That subterranean retreat creates an enormous physical barrier for modern science. Landing a remote-controlled rover on Mars is difficult. Equipping one with a rig capable of drilling hundreds of feet through solid alien bedrock is currently beyond our engineering limits. So while Mars is close by, the chemical fingerprint required to prove life exists there remains buried out of reach. Beyond the asteroid belt, the search for water shifts from sun-warmed surfaces to distant moons heated by internal gravitational friction. Orbiting Jupiter is Europa. From space, it looks like a cracked sphere of solid ice, but that frozen shell hides a massive global liquid ocean. This ocean exists outside the habitable zone due to tidal heating. Jupiter's gravity physically stretches Europa, generating immense friction within the moon's core. That friction produces internal heat, keeping subterranean water liquid and providing chemical energy to fuel complex biological reactions. Yet Europa presents the same logistical roadblock as Mars. Any organisms swimming in that dark ocean are sealed beneath kilometers of rock-hard ice. While Europa proves that the ingredients for biology can exist far from a star, any physical evidence is currently inaccessible beneath the moon's frozen crust. The solution to this extraction problem orbits Saturn. Enceladus is a relatively small, highly reflective moon. Like Europa, it consists of a frozen outer crust hiding a deep subsurface ocean. But Enceladus is actively venting. Massive geysers constantly shoot water vapor and icy particles straight through the crust and out into the vacuum of space. A probe does not need to land or drill to sample this environment. It can simply fly through the plume, open a collection vent, and capture the organic compounds floating in the debris. Nearby, Saturn's largest moon, Titan, offers a much stranger environment. Titan features flowing rivers and vast lakes on its surface, but these freezing waterways are filled with liquid methane and ethane instead of water. If a microbe evolved to survive in a liquid hydrocarbon solvent, its biological machinery would operate completely differently from anything found on Earth. We might struggle to even recognize it as a living thing. Enceladus gives us a clear mechanical path to catch a sample, while Titan serves as a reminder that our definition of biology might be dangerously narrow. Picture the day a spacecraft finally returns data from one of these icy plumes. Engineers analyze the telemetry and find a complex, repeating molecular pattern, a chemical structure that natural geology cannot produce. The first confirmation of extraterrestrial life will likely take this exact form, a microscopic chemical fingerprint, proving that biological processes are happening right now on another world. Discovering a second independent origin of life in our own solar system would demonstrate that biology is a common consequence of physics and chemistry. If it happened twice in a single star system, the probability of life existing across the billions of stars in our galaxy increases exponentially. But a microbe in a dark ocean cannot build a radio transmitter. Identifying simple cellular structures locally does not tell us whether complex, tool-building civilizations are out there. To answer that, humanity must look past the planets and aim our instruments deep into the Milky Way, scanning billions of stars for a deliberate, structured signal. We drill into the ice next door to prove that life is common. We listen to the static of deep space to find out if anyone is listening back.